Hello and welcome again to another Stephen Mendes video. This video is dedicated to my Indian students who have helped to make this channel what it is today. And we have a treat in store for you today. We are going to show you a new method to handle seemingly difficult or impossible networks. Consider the problem in the upper left corner and you will see what I mean. This resistive network does not resolve into simple series parallel combinations which you can reduce. Therefore, to find the resistance requires other techniques. So we're going to use this in a Thevenin problem. Even though we don't need to use Thevenin, we are going to do so. But take a chance, take a moment to inspect the diagram, particularly the pink indication that I have down here. That will show you that it's not as simple as just trying to put it in a series parallel combination. Now, we want to find RTH, which is the dead resistance. We remove the voltage source by shorting it out, which is why you see that in this diagram, we have simply put the 1 ohm resistor across the 4 and 7 ohm resistor and removed the 10 volt source. We have opened where we have the 3 ohm resistor, which is the load that we're using, and therefore we just want to find the current through that load. So the dead circuit is what is shown in the diagram. Now we move on here to discuss a method that we can use to find the exact resistance between A and B. We can excite the dead network with any voltage source and use Ohm's law to find the resistance. That is a simple mechanism because of Ohm's law that directly relates the resistance between the terminals A and B to a current that is flowing when we excite it with a voltage source. So we are going to put a voltage source across the A and B, and then we are going to find the current flowing. Then we're going to divide the voltage by the current, and that will give us the resistance of the network, which is our RTH, or Thevenin resistance. Naturally, we are going to use 1 volt because why not? Unity volts make it easy because at the end we can simply press the reciprocal key and get our answer. Now notice that I have explained using colors how I write my currents and I do my loops, and I have ended up with 3 linear simultaneous equations. It remains for us now to put them into the matrix and solve them to find the current values I1, I2, and I3, which I have done on this page, and it's done in such a manner that students will easily be able to follow what is going on. Now, a quick look back at the diagram will see that the total current that the 1 volt source is providing is labeled I. And if you look a little over to the left, you will see that I divides into I1 and I2. So to find the total, we merely have to add I1 and I2 and then take the reciprocal of that, and that is our RTH, which works out to 7.2 ohms. We now need to find the VTH for the network. So we put back the source, the voltage source, and now we want to see what voltage we actually have at the terminals A and B. So we redraw the network as shown there. You will notice that the 2 ohm resistor connected to terminal A has been removed. And the reason why we can remove the resistor is because we are measuring a voltage. No current is flowing, so the resistance will not alter it. In other words, the 2 ohm resistor would have the same voltage at both ends. So we simply take it out. We have also taken the liberty of adding the 8 ohms and the 6 ohms to get a total of 4 ohms. And we only need now to do some algebra to find out what our VTH works out to be. The total current is easy to spot because we add the 4 to the 1 ohm to get 5, and then we add that series combination to the parallel combination of 7 and 19, which is the 14 and 5 ohm resistor added together. So this is a series parallel combination that's easy to solve. And when we divide the voltage 10 volts by that total resistance, we get the total circuit current, which is I. Now the voltage between point A and point B is going to be the voltage across the 4 ohm resistor and the voltage across the 5 ohm resistor in series. But the 4 ohm resistor has a different current flowing through it than the 5 ohm resistor. So that is the reason for that other equation that you see there. First, we multiply the total circuit current by 4, which is the first thing in the brackets. That gives us the voltage across the 4 ohm resistor. And the other thing on the other side of the plus sign, when multiplied by the current, gives us the voltage across the 5 ohm resistor. We use the current divider formula, which is the other resistor over the sum of them. So if we're trying to find the current through the 5 ohm resistor, we take the 7 and put it over the total and multiply it by I, which is the total current, and then multiply it by 5, which is the branch resistance, and that gives us the total voltage between A and B, which works out to 5.3 volts. Now we take the Thevenin voltage, the Thevenin resistance, and we put a simple series circuit where the VTH flows through the RTH and through our load resistor. And we find our load current to be 0.52 amps. And the voltage across it would clearly be 3 times the current, or 3 ohms times 0.52, which works out to 1.56 volts. Now, the rest of the problem is to prove this method. Prove this method gave us an accurate RTH. That's what I need to do, because for people who do not know the method of exciting a dead network with a voltage so that we may find the resistance of the dead network, they are going to need proof. So the proof of the method is to take the entire original circuit and, not using any other mechanism, see if the current through the 3 ohm resistor matches. So we have taken our entire circuit, divided it into 3 loops, written our 3 loop equations and solved them. And we can see that the current through the 3 ohm resistor is I1. And we see here that I1 has the same value of 0.52 amps. Since I1 is the current through the 3 ohm load resistor, the proof is established. Feel free to use this mechanism anytime in your classes or exams or tests where the network of resistors is too complicated for you to solve by simply rearranging it into series and parallel branches. Thanks for watching the Stephen Mendes channel, and we'll see you soon again.